Okay, so back in Chapter 5, we'd used a random number table actually to randomly select a sample of students. And in Chapter 6, we're discussing a challenging question of probability and determining the probability of events, and understanding the fundamentals behind probability. One of the things that we should understand is that simulation is a very powerful tool in estimating probabilities. And what we mean by simulation is to randomly use some random number generator to observe what happens over many trials and use those observations to predict the probability of some event. So probability through simulation is a little different than theoretical probability, which tells us, or which is a probability in which we look at all of the possible outcomes and determine the number of outcomes that fit divided by the total number of outcomes. And it's also a little different than probability by observation, where we just look back at a lot of different cases and try to make a statement about probability in that way. Probability by simulation is us actually setting up a simulation of the event using some random number generator. So in order to assess this piece as teachers, you have to be able to conduct this piece using a random number table. Using your calculator obviously would be much easier, but we have no way of assessing that on a test at this point. We can't sit over your shoulder and watch exactly what you're inputting your calculator and verify that you're interpreting all of those numbers correctly. So I'm asking you to use simulation, and specifically use the table of random numbers, to answer the question below. Taking a test, multiple choice, in which each question has 5 possible answers, A, B, C, D, E, and one of which is correct. You're guessing. So on every single one of these questions you are guessing, and you are guessing independently of the last, which means if you guess A on the first question, it has no impact on whether or not you're going to guess A or some other letter on the next question. You have no memory of what you did last. So some students might try to trick the system or beat the system by saying, okay, this teacher's only going to put this answer so many times, so I'm not going to guess that answer too often. Well, that's not going to work here. You're guessing independently each time you guess at a question. And I'm asking, what's the probability you get more than 6 out of 10 questions correct? At some point this year, we will learn the theoretical approach to determining the answer to this question. At this point, however, it's a very challenging question. Not only are we looking at the probability of getting 7, 8, 9, or 10 questions correct, but at the same time, we need to look at the probability of getting 0, 1, 2, or 3 questions incorrect and determining where those questions are located. So this is actually a challenging question theoretically, unless we know some special formula. So we're going to answer this question using simulation. Okay? So in order to set up my simulation, I'm going to start by saying, okay, so the probability of answering my question correctly, so I'm going to put plus there, is equal to 0.2. Obviously, the probability of answering it incorrectly is equal to 0.8. And I got that because it's 1 out of 5, right? So I need to set up some simulation using my table of random digits so that those digits are going to represent questions. And the value of the digit is going to tell me whether or not I answered the question correctly or incorrectly. Now, before I start, I need to some way assign correct or incorrect to the values in which I'm drawing. Now, because it's 0.2 and 0.8, it's actually very convenient because I can make 2 out of 10 values correct, and I can make 8 out of 10 values incorrect. I could actually use any fraction that is equivalent to 2 out of 10 or 8 out of 10. So if you're wondering, could I do 1 out of 5? Well, the answer is yes. But I like using 10 because now I'm going to choose from 10 possible values. In other words, as I look across my table of random digits, each value, 0 through 9, is going to represent an outcome. And obviously there are 10 values from 0 to 9. Well, now, in advance, I'm going to assign 2 of those values, let's say 0 and 1, as correct, and all of the remaining values are incorrect. So 0 and 1 represent a correct answer, 2 through 9 represent an incorrect answer. Now I'm going to go up to my random number table, starting at some random line number. So I could start at line 104. I'm just going to start at the left, just to be simple, and I'm going to group my values by 10 to represent the 10 separate questions. Now obviously in this case I have to allow for repetition. If I avoid repeating a number, well then every time I choose 10 values I'm going to get exactly 2 correct. It's equally likely that I'm answering the same answer. It's equally likely on each question that I get it wrong or right. So I need to allow for repeating values. So looking at this table, okay, I'm going to go right across. Incorrect, 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 incorrect. Now let's go right for the clean sweep. So out of 10 questions, I had all 10 wrong. So currently, I have conducted one trial of 10 questions, and the probability that I got more than 6 out of 10 right is 0. Because in one trial, I had 0 probability of getting more than 10 correct. Law of large numbers states that over a small number of trials, some strange things can happen. However, over a large number of trials, what should happen will happen. So one trial is not enough. I've got to repeat this. Theoretically, I've got to repeat this many, many, many times. So let's go ahead and do a second trial. So I'm just going to keep moving along. I'm going to pick the next 10 values. Okay? Correct, correct, correct. So now this second time, I had 3 out of 10 correct. So after trial 2, well, I still don't have any in which I get more than 6 out of 10 questions correct. So I'm still at 0 out of 2. So my probability is still approximately 0. So in trial 1, I had 0 right. In trial 2, I had 3 right. Okay? I could continue this on. So I'm going to do a couple more trials. That's an awfully great result, having half of them correct. But, unfortunately, still not meeting my goal. I'll try again. And in this case, I only get 1 of them correct. So this time I have 1 right. I'm still not meeting my goal. I'm going to try one more time. And in this case, I only have 2 right. And yet, I am still not meeting my goal. Is 5 trials enough? No, it is not. Okay, it is not enough for the experimental probability to more closely resemble the theoretical probability. For now, I can say that I'm pretty sure my probability is very small, something awfully close to 0. In hindsight, I wish I had set this problem up so we could look at getting more than 4 out of the 10 questions right, something that was a bit more realistic. Okay? What I would need to do from here is I would need to do many, many, many more trials. Hundreds, perhaps, to try to get closer to what the expected probability should be, the theoretical probability should be, and to get farther away from this small experimental probability. So again, from this point, I will do tens, hundreds of more trials, and keep track of the number of trials in which I had more than 6 out of 10 questions correct, and divide that by the total number of trials that I conducted.